Hello, I'm Walter Lewin. I teach physics at MIT, which is the Massachusetts Institute of Technology, which is located in Cambridge, Massachusetts in the United States. Before you watch this presentation, you should have familiarized yourself with four concepts: torques, moment of inertia, angular velocity, and angular momentum. I wrote them down for you. Torques, notice I started the word torques with the Greek letter tau. We often use in our mathematical equations tau for torque, so that's why I thought it was funny to put a tau there. And here you have moment of inertia, here you have angular velocity, and here you have angular momentum. So if you're not familiar with these four subjects, then you should not yet watch this presentation. First do your homework, and maybe later on in the course you can watch this program. So for now, over and out, and I'll be back very shortly. Suppose we have a spinning object which has moment of inertia about the axis of rotation, I, capital I, and angular velocity omega. Then the angular momentum L, which is a vector, equals I, which is the moment of inertia, times the angular velocity omega. L is a vector, and omega is a vector. And the direction of the vector omega, and therefore the direction of the angular momentum L, depends on whether the rotation is clockwise or whether the rotation is counterclockwise. I want to demonstrate this to you, to show this to you with this example. I have here a potato, and I have a right-handed corkscrew, and I'm going to turn this corkscrew clockwise as seen from this direction. Notice I turn it clockwise. And what you're going to see now is that the corkscrew is going into the potato and is coming out on the other side. There it comes out. So a clockwise rotation moves the corkscrew in this direction, and that is our convention for omega. So if the angular rotation is in this direction, then omega is in this direction. If now I go counterclockwise, you see that the corkscrew comes out, and so now the angular velocity omega is in this direction, and therefore the angular momentum is also in this direction. The corkscrew is now coming out of the potato. If no external torque acts on the object, then angular momentum is conserved. Let's take a situation now whereby angular momentum is conserved, but whereby the moment of inertia changes. If the moment of inertia changes, and if angular momentum is conserved, then L is not going to change. I is going to change, so omega must change. I would like you to think about this a little bit on your own. Is it possible that angular momentum is conserved, and yet that still the moment of inertia changes? And what are the consequences of that? And while you're at it, I would like you to also brush up on the concept of the conservation of angular momentum. In other words, discuss with your peers and with your teacher what are the conditions when angular momentum is conserved, and under what conditions is angular momentum not conserved. So discuss this, stay tuned, and I'll be back with you shortly. In the absence of external torques, angular momentum is conserved. So let's look again at this equation. If there are no external torques on the system, L remains constant. So the product I, omega, cannot change. Suppose now I goes up by a factor of 3, becomes 3 times larger somehow. That means omega must then decrease by a factor of 3. Suppose we have a situation whereby the moment of inertia goes down by a factor of 1,000,000. That means omega must now go up by a factor of 1,000,000. Would you be able to come up with some examples whereby angular momentum is conserved, or is conserved to a very good approximation? It doesn't have to be exactly conserved, but to a very good approximation, and whereby the moment of inertia is changing significantly, which, as we just discussed, must give rise to a significant change in omega. So discuss this with your classmates and with your teacher, and try to come up with some nice examples. Stay tuned. I'll be back with you shortly. An example that comes to mind, at least it comes to my mind, is the core collapse of a massive star. In the process, a neutron star can be formed. And a neutron star has a radius of only 10 kilometers. And the moment of inertia of a rotating star I is proportional to the radius of the star squared. And therefore, in this core collapse, the moment of inertia can easily decrease by a factor of 1,000,000, and that would mean that omega would have to go up by a factor of 1,000,000, and that's the reason why there are so many very fast rotating neutron stars. Another example that comes to my mind is that of an ice skater that is turning around like this. And so the ice skater can have her arms spread out like this, and she can bring her arms in like this. And as she moves her arms out, her moment of inertia will increase, so her angular velocity will decrease. And as the ice skater brings her arms in, the moment of inertia will go down, and therefore her angular velocity will increase. I'm going to demonstrate this with you in a way that is a little bit more convincing than if I just were to move my arms in or out. I'm going to hold, or not I, but my graduate student Joel is going to hold in each hand a 2 kilogram weight. And so we now hold in each hand the 2 kilograms, and then he will stretch his arms outwards when you will see his angular velocity decrease, and then he brings the 2 kilograms inwards and you will see his angular velocity will increase. And so our task is now, our first task is to calculate the moment of inertia, or the approximate moment of inertia, of a person who is just standing straight up with her arms down. So this would be the person, and her arms would be down like this. And this person would be rotating about this axis. So discuss this with your teacher, discuss this with your classmates, and see whether you can come up with a rough estimate. It doesn't have to be very accurate, with a rough estimate of the moment of inertia of a person standing straight up about the axis of rotation. Stay tuned, and I'll be back with you shortly. Okay, so I'm very curious to know what model you came up with to calculate, to estimate roughly the moment of inertia for an object which is spinning around. I'm going to propose to you a cylinder, so I approximate the human body by a cylinder, and the cylinder has a radius r and has a mass m, and the mass is about 75 kilograms, not an unreasonable mass for a person, and let the radius of the cylinder be about 0.2 meters, about 20 centimeters. So the cylinder we're going to rotate about the axis of symmetry. We do not have to specify the length of the cylinder because the moment of inertia is independent of the length. The moment of inertia for rotation about this axis equals 1/2 m times r squared. If I substitute 75 for m in this equation and 0.2 for r in this equation, then I find that the moment of inertia is about 1.5 kilogram meter squared. Now I'm going to calculate what the moment of inertia is of this person, of this cylinder, when the arms are stretched and when at either end, at both ends of the arms, is a mass of 2 kilograms. In other words, I have to add to the 1.5 kilogram mass meter squared, I have to add the mass of 2 kilograms times this distance squared, and we will make an assumption, an estimate, that the distance from the 2 kilograms to the axis of rotation is about 1 meter. Nice number. So now we can calculate the moment of inertia when the system is like this, with the arm stretched, the cylinder, plus a weight here and a weight here. And that moment of inertia is now the 1.5 plus the 2 kilograms multiplied by the distance 1 meter squared. And since there are two objects, I must multiply it by 2. And then I come up with about 5.5 kilogram meters squared. You see that these two weights, 2 kilograms here and 2 kilograms there, make a huge difference in the moment of inertia of the person, as long as she has her arms stretched. Now what we're going to do, we're going to calculate the moment of inertia when the person has her arms down or her hands very close to her body, and we will assume that when the person pulls her arms in, that the two masses are at a distance capital R, which is the 0.2 meters. So we're going to recalculate now the moment of inertia. This was the moment of inertia when the arms were stretched, and now I'm going to calculate the moment of inertia when the two arms are down. So we get the 1.5 plus 2 times 2 times 0.2 squared. And that is about 1.7 kilogram meters squared. Notice that it is not very much larger than the 1.5 that we had earlier. The reason, of course, is that we bring these two masses now so very close to the body. But, and this of course is key, the 1.7 is about 3 times smaller than the 5.5. When the masses are here, stretched, the angular velocity will be 3 times lower than when the masses are here, when the moment of inertia is 3 times lower. And so as this ice skater moves her arms from this position to this position, her angular velocity will change by a factor of 3. And this is what we're going to demonstrate this to you. My graduate student, Joel Frederickson, will be put on a turntable which rotates with near zero friction, not exactly zero, but almost zero friction. That means there will be no significant torque on Joel. We can ignore any torque, any external torques, and therefore angular momentum is conserved. And if now he is going to stretch his arms and pulls his arms in, you're going to see the result of the change in angular velocity. With his arms stretched out, his angular velocity will be 3 times lower than when he pulls his arms in. This demonstration is called Ice Skater's Delight. I want you to realize that it is not a delight at all. You can get very dizzy. If you bring your arms in, there's a sudden increase in the angular velocity which can make you dizzy, and then you can fall. But I will be very gentle on Joel. I recommend that you do not try this on your own. If you try this ever on your own, make sure that someone is helping you, because I'm not joking when I'm telling you that you can get very dizzy and you can fall and you can hurt yourself. So I'll be very gentle on Joel as we start this demonstration. All right, here is Joel, my graduate student, Joel Frederickson from Iceland. And I have here the 2 weights, one 2 kilogram weight and another 2 kilogram, one in left and one in his right hand. And we're going to put him on this turntable. It's a little risky. Are you comfortable, Joel?
I am.
Okay, how do you want to start? With your
arms outstretched, I think.
You want to start this way? Okay, I'm going to give him a very small angular velocity, and then we will redo the demonstration with a little bit larger angular velocity. So there he is going, and now he's bringing his arms in, and you see he's going faster. He's bringing his arms out, and he slows down immediately. Okay, now we're going to be a little bit rougher on him. We're going to give him a slightly larger angular velocity, and he's going to try it again. There we go. He brings his arms in, and he's going much faster. Whoa, boy, you're going fast. Gee, are you okay?
I'm fine.
He's fine. And now spread your arms out again, and he slows down. Great. So now make sure that he is not going to fall off. I will first take the 2 weights from him, and then I will help him down. Great, thank you very much, Joel. That was terrific. Hello, I'm back. I got a haircut. I hope you still recognize me. If you want to learn more about angular momentum, about the conservation of angular momentum, about stellar collapse, which causes a supernova explosion, if you want to learn more about fast rotating neutron stars, I recommend you watch 2 of my lectures which you can view on the web. And one lecture that you may want to watch is number 20, lecture number 20 of my lecture series of my course 801. And you can view that on MIT's open courseware, for which we normally write OCW. That's one lecture. And the other lecture is not on MIT's open courseware, but is on MIT World. And that lecture has the title Birth and Death of Stars. I really recommend you watch these 2 lectures, and you will get a much better appreciation of angular momentum, ice skater's delight, and core collapse of massive stars. There's one more point that I wanted to make, and that has to do with the calculation of the moment of inertia of a spinning person. When Joel was standing on the turntable, I did not take into account the moment of inertia of the rotating table. And there was a reason why I didn't, because the contribution of the moment of inertia due to this rotating turntable is so small that it can be ignored. The turntable has a mass of about 4 kilograms, and it has a radius of about 20 centimeters. And since the moment of inertia of a solid cylinder is 1/2 mr squared, m being the mass, r being the radius, the total moment of inertia of the rotating turntable is only something like 1/10 of a kilogram meter squared. So it's clearly negligible. So I gave you and I discussed with you 2 examples whereby angular momentum is conserved and whereby there is a change in the moment of inertia which leads to a change in angular velocity. And I was wondering whether you perhaps can come up with some more examples. I was only able to come up quickly with 2, but there must be many more. And this may be a nice exercise for you to think about more cases. Of course, angular momentum doesn't have to be exactly conserved, like the case of the ice skater's delight, as long as it is approximately conserved. So if you can think of some examples, let me know. Send me email. My email address is Lewin, this is an E, at mit.edu. I'd love to hear from you. Good luck.